Okay, something's wrong here. Okay, to work some of these problems. I'm going to graph one of these exponential functions. I'm going to do it like this. Oh, I kind of missed some of my points, but you get the idea. Okay. That's a shape of any exponential function if it doesn't have a vertical shift. Okay. Always. So now what I want to do is I want to say, well, okay. It has no number out in front of the 1.7 to the x, so I know that if x equals 0, y is going to be 1. So I know that I have a 0.01. Then I know that I'm going to have the 1.7. Well, where's 1.7? 1.7 is here. Let's say that's positive. So here's where x equals 1. Now, I originally scrapped this using my basic values, but I didn't label the x-axis. I didn't label the y-axis, although I'll be able to use my label for the y-axis. Okay, since what is going to be 0, 1. So in here I got 1, 2, 3, 4 on the y-axis. I can ignore the marks I used on the x-axis to graph the basic exponential function. That can make those marks very light because we know how to graph this and we can graph this thing quickly. If x equals 1 here, and I guess x equals 2 here, and we could go out to x equals 3 here. And then we have x equals -1 over 1 here, and x equals -2 over down here. Okay, that makes sense. You've got the shape of the graph. You can always graph the shape of an exponential function just using your basic values. And you don't usually want to graph the thing too far to the left because it gets really small, or too far to the right because it gets really big. Now, there might be cases where you want to go another unit out to the right, but that puts up off the board, one up and down here. Oh, yeah, okay, maybe it goes on up. Okay, it starts getting very, very steep. So the graph shape isn't going to be particularly helpful to you if it gets too close to the x-axis or if it gets too steep. And it does both very quickly. Okay. So let's just estimate. Okay, for my graph, if x equals 2, failure 1. Well, we can come over here and we can, it looks like it's pretty close to 3. Okay. Which would mean that 1.7 squared is going to be pretty close to 3. So 1.7 squared would be about 3. Maybe a little less than 3, maybe a little more. Well, it's easy to square 1.7. If you know your multiplication table's up to 20, you know it's 17 squared is 289. So 1.7 squared is 2.89. Meaning 3 wasn't a bad estimate. Okay. Now you don't want to do everything by estimates. You want to be able to figure out the numbers, but it's pretty easy to figure out what 1.7 squared is. You can do it by hand, you can do it by calculator. You can raise 1.7 to the power very easily. How about the solution to the equation? How would you solve the equation 1.7 to the x equals 2? Well, you can solve it algebraically. You have to use your calculator at the end, okay? Yeah, I think we've seen the rules you need, but and I apologize, I didn't review what we did last time, so I don't remember if I did that in this class or the support class. In any case, I'm going to show you. Okay, but according to the graph, what would it be? What's it look like? Write down a ballpark figure on your paper. Okay. Solution 1.7 to the x is 2 means find the x value that makes y equal 2. Because of course, this is your x value, this is your y value. So it's going to be a y value. Because of course, the graph shows you the values of 1.7 to the x, at least just some kind of an approximation. So 1.7 to the x equals 2 means you go over here to 2 and you find the graph point. The line y equals 2, right? And that graph point will be here. And you project it down. Now, according to my picture, it looks like about 1.2. Remember, I kind of missed my point here, so my graph's probably a little bit too steep. So according to this graph, using these projection lines, we see that x is maybe 1.2. Okay, we'll check out that estimate. A lot of you have your calculators handy. It's 1.7 to the 1/2 power. And if my estimate is any good, which it probably is, and I think I like yours better, but is 1.7 to the 1.2 close to 2? It's reasonably close. It's about 1.9. Hang on here. Okay, so what people got on their calculator, 1.7 to 1.2, at 1.89 something, we'll say it's about 1.9. Okay, so that means 1.2 wasn't a bad estimate of the solution. Somebody else said, well, I tried 1.3 and it's closer. Yeah. And I'll bet you 1.4 is maybe 2.1 or so. Okay. So 1.2, 1.3, 1.4 all give us results close to 2. And of course, we're looking at a hand-drawn graph. In my case, there's some flaws in the graph that made me go a little bit low. In your case, there might be flaws in the graph that made you go a little bit high, or maybe you just made a, your estimate just a little bit off. Okay, that's okay. The graph gives us an approximation. Now let's find out what the value actually would be. Okay, we want to actually solve 1.7 to the x equals 2. The equivalence between logarithmic and exponential functions, okay, is the log, first log base b of a equals c means b to the c equals a. Now, did we do this in class? Okay, you haven't seen it before. Okay, that's kind of what I was suspecting. As I say, we're moving a little further ahead, but not as deep in the support class. And unfortunately, I just overlooked the whole idea of reviewing what I did last time. Okay. Okay, now I'm not going to put all this on the recording because it's pretty simple. You understand that here's our table of the 2 to the x function. So here's the table of the inverse function. I just flipped the columns, switched the columns, inverse the columns. And if I graph the result, the graph is going to look kind of like this. And you're going to see that as you get into the logarithmic functions. So here is the graph of the inverse of the 2 to the x function. So we can now say that this is a table for the graph of y equals log base 2 of x. We're going to be able to use logarithmic functions to solve equations like 1.7 to the x equals 2. By translating a function, 1.7 to the x equals 2 is like b to the c equals a. All right. You know, b is your 1.7, x is your c, a is your 2. If I put the function in this form, I get log base 1.7 of 2 equals x. Now, you don't necessarily have to follow that right away, but if you write out what b is, what c is, and what a is, and then just write this out, you get it. And the neat thing about it is you have a log key on your calculator, just like you have an e to the x key or a b to the x key, you have a log key. So you'll be able to use that. And this is kind of an overview of one of the most important things we do with logarithmic functions. There's plenty more to learn about them. Take us back to the The other important property, the one I like to introduce first, rather than some simple rules for manipulating logarithms, is that what do we mean by log base of b of a? Log base b of a. Well, that means That's log of A divided by log of B. Okay, so these are two things I want you to understand. This is just an expression of the fact that the log is inverse to the exponential function. And this is an important thing for making calculations. Now, most calculators actually have a button on them that you can just put in log base B of A and punch a button and it comes out. So calculators go to calculate it very easily. When you write it out, I want to see log of A over log of B. We'll see that with a couple of examples. Point then is, I've got a method for solving this equation. So let's go ahead and actually solve this equation to see how it works before we really get into it. So let's use these properties to solve. One point seven to the x equals 2. Okay, well, the question is exponential equation. Is this equation in this form or is it in this form? How many think it's in this form? How many think it's in this form? How many understand that if I've got it in this form, I can put it into this form? So right here's your rule. Okay, that's really simple. You got to be careful. So what we want to do here is, this is a form. B to the C equals A. What's the value of B? What's the value of C? What's the value of, I want you to write this down in your paper. B equals what? C equals what? A equals what? It's the simplest possible answers. Okay, I think everybody's got it, but let's be sure. B is what's being raised to a power. That's the same as 1.7, so B is 1.7. C is your exponent. Here's your exponent. Here's your exponent. C is X. A is what's on the other side of E. That's fine. That's 2. I think everybody sees that. Okay. Well, the equivalent form is log base B of A equals C. So can we take this value of B, this value of C, and this value of A and plug it in here? Please do that. Some of you have already done it. Some of you already got a solution. Let's make sure everybody's on track. Okay. What we get, and I think everybody's got it, is log B. Be careful here. These are 1.7. I'll keep it colorful. Color chalk. Log base 1.7 of A, which is 2. And that's equal to what? That's equal to C. And happily, C is X. So now we have a solution for X. That is a solution. Because that is something you can just punch right into your calculator. Okay. And this is the exact solution. So the exact solution is then X equals log base 1.7 of 2. Now, how do you get a value for that? If you want to approximate it, because in general, you're going to be dealing with approximate solutions, because solutions of most logarithmic equations are irrational numbers. You've got to approximate them because they go on forever. Infinitely long decimal expansion. No discernible pattern. So what do you do to evaluate this? Well, you use this. Okay. So at this point, I would want you to actually write it out. X is log of 2 divided by log of 1.7, that parenthesis. And now you've got an LOG button on your calculator. So you write out what's a log of 2, what's a log of 1.7. Log of 2 somewhere around 3, pretty close to 3. Log of 1.7 is somewhat less than 3. Okay, that's very good. Everybody got it. Log of 2 is approximately 0.3. And the log of 1.7 is approximately 0.23. And this gives us something approximately 1.3. You can do it as many significant figures as your calculator will allow you if you want to be really precise. But your calculator is going to give you way more significant figures than you'd ever need for real world calculation, unless you're a part physicist or something. Okay. So there we have it. Now that's a pretty simple process in the sense that you've got a couple of rules here. Use those rules and boom, you've got a solution. And if you do this, half a dozen times, you know how to do it. Then if the test comes up, well, you review it, okay? And you're able to do it. It's one of the easier things you'll be tested on. Okay. And then later on, of course, you take calculus and have to deal with logarithmic functions. You'll forget it, but it'll be there because it's pretty easy. Review it, and it'll be there again. Maybe you won't forget it. Okay. But give us how much you practice. All right. Well, let's go back to our original question. Now, to get all that just from this one question, we graph this thing. Okay, we graph it. We see a certain technique for graphing it. There are other techniques. But I like the idea of just getting to graph your basic function. If you want to extend out to x equals -3 and x equals 3, you can do that. You go much beyond that, the graph gets too small or too steep. That really be very useful. Still good for visualization. How would you do 0.6 to the x? Well, 0.6 is less than 1. And you know from the homework that if you graph an exponential function with a base less than 1, it's going to be a decreasing exponential. So you want to draw a graph. And I'll make my arcs here pretty small since we're not going to really use them. If you understand what I'm doing, because you've done this a whole bunch of times, I hope. So here we've got, my hand gets in the way, I can't see the points that I'm aiming at. Here we've got a decreasing exponential function, okay? Now, this is going to be particularly useful for graphing this. Because when x equals 1, y is 0.6, which would put it, okay, x equals 1 here. Sorry, y equals 1 here. So y equals 0.6 about here. So my x scale, if I use this graph, probably put x equals 1 here, and all my values are really low. Okay. So what I'm going to do is I'm just going to shift this graph to the right. Still graph with an exponential function. But since most of our significant values are going to occur to the right of the x-axis, it's going to be valid to do that. So what I'm going to do is I'm going to erase this. I'm going to erase my original y-axis. And I'm going to put my y-axis over here. I can do that. It's still an exponential function. And it's got no coefficient out in front. 0.6 to the 0 is still 1, right? Now, this value was 4 when I did my original function, but now it's 1. So here's the 0.01. Now, if I want values, the negative values of x, well, they're going to go pretty fast. If I want those, well, I just want it. Okay. I maybe use different techniques for doing the graph. But now, how am I going to label? I've got a scale for my y-axis. How am I going to get a scale for the x-axis? I know the point for x equals 1 is going to be y equals 0.6. Well, here's 0.5. So thinking 0.6 will be about here. So I just project over and down. And right here is where x equals 1. I'm not going to require you to be able to do this, but it's a handy way to relabel a graph that has a nice exponential shape so that it works for you. Okay, so using a graph, can you estimate a solution to the equation 0.6 to the x equals 0.3? Okay, people do quite well. I think everybody pretty well sees that if this is 0.6, well, we can do a little more scaling and we can see that y equals 0.3 and on this line. It just happened to go through one of my dots, so it wasn't intentional. But now I can project down to here, and here's my solution of the equation. 0.6 to the x equals 0.3. Now, what's the value look like? Yeah, there's 1 and another 1. Actually, I do the graph kind of carefully, so it actually kind of works out. And it looks to me like that's x equals 2. Okay, that's not totally accurate Because 0.6 to the second power is what? Well, hold that thought for a minute. Estimated solutions x equals 2, right? Because it really, I mean, if I do it honestly, it might be just a hair bigger than 2, but pretty close to 2. Okay, do this in your head. What's 0.6 squared? Okay, well, 6 times 6 is 36. 0.6 squared is going to be 0.36. Not bad for a graph. Now, all the stuff I did to create this graph of the decreasing exponential, you can always create a graph of a decreasing exponential by putting a point on the y-axis and then going down to half that value and moving over some distance. And then by taking half of that value, we'll go over the same distance. So if you move the same distance along the x-axis every time, your y-axis always, or your y value always becomes half as great. That's equivalent to sketching a graph of the basic exponential function. And of course, if you go 1 unit to the left, you got to have a point that's twice as high as this one. So you can look right here. Okay, so you can always kind of slop down a graph of an exponential function, increasing or decreasing, depending on your base, and adjust your scale as appropriate. So I want to stay under. Okay, now we could solve this. Now, when you're first doing this, you want to go through the whole process of identifying your A, B, and C, or whatever, in your forms of your basic exponential log, or your exponential logarithmic function. And using the same thing that we did over here, without going into all the detail, this says that log base 6 of 0.3 should equal x. So that x equals log of 0.6 over the log of 0.3. So punch that into your calculator. Now that's very simple. Once you've done this a few times, it almost becomes automatic. You just got to be careful. I should have followed my algorithm there. I know better. I wrote it down too quickly. It's log of 0.3 over log of 0.6. The other doesn't make a whole lot of sense. Yeah, log of this over log of this. Okay. Okay, so what do we get? Like 2.35 or 2.36. Probably rounds off to 2.4, so I'm just going to use 2.4. So we estimated 2. Our actual was between 2.3 and 2.4. Okay. I say that's not bad. We could have used a better graph, maybe used it more carefully. We don't really need to use a graph to do these things, but you want to be able to picture what your equation is telling you in terms of a graph, because the behavior of exponential and logarithmic functions will, if you understand the behavior of these things, it's going to give you advantages, not necessarily in what you do for a living, but just in your financial world. Okay. You want to think in terms of investments. You want to start thinking in terms of investments now. Even if you don't have a lot of money, you want to be thinking of what you're going to do when you get a little bit, and the idea of how investments grow and so forth, and make intelligent decisions. Intelligent decisions that you make not because somebody tells you this is what you need to do, because different people might tell you different things, but make an informed decision. Is it what this person's telling me reasonable? It probably is. There's a wide range of what's reasonable, but the better you can make your own decisions, the better those decisions might be. Also, again, in almost every field, exponential behavior is really important. So we really do want to try to understand it. Okay, now just a little bit more about the graphs. What do we do with these graphs? That f of x equals 2 to the x plus 5. I say we're going to take our basic graph, and if we use our basic values, the range of 2 to the x is from 0 to 4. So the range of 2 to the x plus 5 will be from 0 to 9. 8's kind of a convenient thing to subdivide. So 9 will be about here. 4 will be about here. Okay. So we're going to have our standard x scale in this case, to the negative 1, 1, 2. And we're going to have our usual graph of 2 to the x. So there it is. If you want to go out to x equals 3, there's room up here. Okay. Why not do that? If you've got the basic graph, it's really easy to see how it extends. So that's going to come up here to x equals 8. And get some point here. No point in going to negative 3. It's already too close to the x-axis. Okay. Now, what are we going to do now? We're going to raise every point of the graph off 5 units, because we start with y equals 2 to the x. It's going to be this. If we do now y equals 2 to the x plus 5, all our y values become 5 greater. So we raise this point up here. And there's an arrow of length 5. And then we just do the same arrow on every other point. And I'm not doing this with whole lot of. Here. I have points here, here. We can actually look at there. There's a reasonable graph of 2 to the x plus 5. Now, if we have a times 2 to the x minus b, what are we going to do about that? Wait. Anyways, you can do that. We're going to be multiplying the values of 2 to the x by whatever a is. Okay, so let's say we have f of x equals 4 times 2 to the x minus 7. It helps to see what the range of this function is going to be on our domain. In this case, the basic domain. Well, 2 to the x goes up to 4. Range of 2 to the x is 0 to 4. And multiply my y values by 4, it's going to go from 0 to 16. So if I want a graph of 4 times 2 to the x, I'd better go from 0 to 16. I want to have 16 up there, so it's going to be here. 4 is going to be here. Now my basic graph will be these points, so I can draw my basic graph. It's kind of flat, but you can see the curvature, especially when you get out here. Okay, so here's my y equals 2 to the x. 4 times 2 to the x, every x value gets multiplied by 4. That means we move every point 4 times further from the x-axis. So now, my transformation is going to look like this. We're going to have this. We're going to have another one, another one, and another one. So this is my position relative to the x-axis. This arrow or vector tells me how to move from here to here. Then I've got to move that far, and that far again. It puts me upward. Okay, well, I do the same thing here. That's not far, so I can move 4 times that far. It looks like this. 0 is too short for the right distance. I'm fudging a little bit. It's a little hard to do this actually with a small graph. Okay, it's going to move us up to here, here, and here. Then we move here. Smaller moves here, and even smaller ones here that I can't control. So here's my y equals 4 times 2 to the x. And then what do I have to do? I got to take it 7 units lower. So down 7 units. Down 7 units. Wait a minute. 7 units there. Okay, then come down 7 units. This one. And down 7 units. And down 7 units. And there's my y equals 4 times 2 to the x minus 7. Okay, well, you should be well prepared to graph these things by transformations. Um, a graph of y equals 2 to the x, not a great graph, but you understand how to do the graph. I want to do y equals 3 to the x. Well, 3 to the 0 is still 1. 3 to the 1 is 3. So this point's going to be a little higher. And 3 to the second is 9. That's going to be up here. 3 to the negative 1 is 1/9, which is somewhat less than 1/4. Only about half as great. And 3, I'm sorry, it's 1/3, not 1/9. 3 to the negative 2 is 1/9. So here's a graph of y equals 3 to the x. Now, e is a number, and I'll probably talk next time about what e has to do with exponential functions. Most important number in mathematics by most estimations. Approximately 2.718. Now, is e closer to 2 or 3? Tell me, which one's it closer to? It's closer to 3. So the graph of e to the x is going to probably be closer to the graph of y equals 3 to the x than it is to the graph of y equals 2 to the x, but not all that much closer. So in between these two graphs, I've got y equals e to the x. Okay, well, as you see, log base 2 of x is inverse to the 2 to the x function, right? And log base 3 of x is inverse to 3 to the x. Log base e of x is inverse to e to the x. Log base b to the x is inverse to b to the x. Okay, there's a pattern here. Log base e of x is ln of x. You have an ln of x button on your calculator. Very handy because a lot of times exponential functions are written in terms of base e, which has some really convenient properties, especially when you get to calculus. It's really easy to do derivatives of e to the x functions. A little more complicated if it's a 2 to the x or 3 to the x. It's very, very natural. It's called the natural logarithm. And e is, in a very real sense, we'll talk about next time, most natural base for exponential functions. 2 is a convenient base and it has a lot of good properties. And that's the base we've been using. But kind of the universal base is e to the x. And again, that's because it's really easy to do calculus with an e to the x function. Much harder to do it, a little harder, a little messier to do it, not much harder, but messier, less convenient to do it with a 2 to the x or 3 to the x or 0.7 to the x function, okay? So there are good reasons that we want to talk about the exponential, basic exponential function, and you'll see some of that in your assignment. If you understand everything we've done here, I think you'll find the assignment to be fairly straightforward.